Okay, what the heck are eigenvectors and eigenvalues? Here's a big thing. When you have a matrix like this, a 2 by 2 matrix that we call a transformation matrix, it will do something to any vector that you put into the plane, okay? So in this case, I do 2 times x plus 0 times y, so I get 2x plus 0y. And then I'd have 0 times x and 3 times y, I get 3y. So this matrix would stretch every point in the plane 2 by a factor of 2 in the x direction and a factor of 3 in the y direction. And you could apply this to any point you want, right? That's why we've got the x and the y here, literally the entire thing. So one thing that you could think about, or one way you could think about this, is if you thought about it's stretching the plane kind of like this. Now this is not the same matrix as we have here, the 2, 0, 0, 3. This is, baby seal says hi, the matrix 3, 0, 1, 2. And so this matrix right here, you'll notice it stretches the entire plane so that you end up with this turquoise grid. Sorry, baby seal is trying to get your attention. Everything's fine. Okay. Okay, so when you do that kind of stretch, this happens to almost every single thing in the plane, where you've got this vector, this yellow vector that's on what's called span, and then as you stretch it and you adjust things, where like you apply this matrix to this yellow vector, it's gonna get knocked off what we call the span. The span is like the line that runs through the original vector. That happens to almost everything, okay? There is a super special case, and it gets to be called, you guessed it, an eigenvector, wherein a vector gets stretched by the same grid, but it doesn't leave its span. It stays on the span. Those are eigenvectors. And in this case, this one went from 1, negative 1 to 2, negative 2. It is now twice as long. Its eigenvalue is 2. So one way you could think about this, and this is oversimplified, but it is the right idea, is that an eigenvector gives you a direction. It means like, go here, look that way, look that way. And an eigenvalue describes a stretch in that direction. So how far did it move? 3 times as far? Did it move 6 times as far? What was the stretch that you got in that direction? Maybe it moved negative 2 times as far, meaning it kind of like turned around. Okay, so how do I go about calculating these things? This equation right here is a really important one, because this is really how we're going to get to the eigenvectors and the eigenvalues. A is a matrix. This is really important, because when I first see this equation, I'm always like, oh, A and lambda are the same thing, but they're not, and that's kind of the whole point. What we're looking for is a matrix multiplied by a specific vector that is equal to a scalar, so this is just like a number, like 2, 7, 8, 4, and multiplied by the same vector. So to be very clear, this yellow vector is the eigenvector, and the green scalar is the eigenvalue. That's what we're looking for when we do this. So all we get to start out with is a matrix, and our goal is to find the eigenvalue and the eigenvector that will make this true. So, and I mentioned that again here. So basically what we're looking for is, here is the matrix, vectors, value. Another way that you guys could write this is like this. Mathematicians are lazy, and so we tend to write shortcuts whenever we can. So here's my shortcut for a vector, and because your book is a jerk, and because mathematicians are the worst sometimes, even though I love them, they used like a bold X, that's why I've got the little arrow over this, to stand for the matrix XY. But really what we're doing is we have this matrix, and we are looking for some vector multiplied by some scalar such that this equation is true. So that's our goal. Okie dokie, moving along. To solve for this, I'm going to subtract lambda x, lambda the vector x, from one side. So all I've done is that. That's where the 0 comes from. Then I need to get the lambda to talk to the matrix. And in order to get the lambda to talk to the matrix, because a single number, you can't subtract a number from a matrix, but you can multiply by 1. Remember, this identity matrix is just like 1. And then you could distribute the lambda to this identity matrix. This is just scalar multiplication. Now I've got a matrix, and they can talk to each other. That's good. We want that. So I'm going to factor out the vector x. So now I just have two matrices. I can combine them just using subtraction. So here's me combining them using subtraction. 1 minus lambda, 4 minus 0 is 4, 2 minus 0 is 2, 3 minus lambda is 3 minus lambda. Now it's looking a lot simpler because we just have a single matrix and the vector is equal to 0. Oops, wrong thing. Okay. And just so you know, just like before, this is what we've got. We've got a matrix, a vector, which actually looks like this, and it's perfectly fine to write 0 as the 0 vector of 0, 0. This, happily, gives us a way to solve for lambda and a way to solve for this vector. So a really boring solution is when you let x equals 0 and y equals 0. That would get you an answer, but not be very helpful because that's just going to flatten everything to a single point, and that's not useful. We're looking for a vector, right? So another way that we could solve this is if we can get the determinant of A, this matrix, to be, so why do I have that labeled as K? Ignore me. We get the determinant of A to be equal to 0. Now you might reasonably ask, why would I want that? Very reasonable question. Here's what I will say. If you watch the 3 blue 1 brown video, he talks about a squishification to a single vector from 2 dimensions into 1 dimension, and that's really kind of what we're doing. Yeah, watch that video. Let me know what questions you have from that. I know this is a little iffy, but it's hard without all of the linear algebra background that one probably should have for this, which is not your fault. Oh, okay, so now we're going to solve this. To get the determinant, what we're going to do is we're going to take these multiplied and then these multiplied, and we will subtract off the 8 that we get from this. So we write this like this. So we've got 1 minus lambda times 3 minus lambda minus 4 times 2, which is our 8, is equal to 0. And hey, this is just a quadratic. And you guys know how to deal with quadratics. That's not so bad. We distribute, we gather our terms, we factor, and you get that the first value of lambda is -1 and the second value is 5. Now that we have the lambda value, so these are our eigenvalues. Boom, eigenvalues, guys, we did it. Yay! Eigenvalues. And with each eigenvalue, we need to find the eigen... Oh, goodness gracious me. That's not what I wanted. With each eigenvalue, we need to now find the associated vector. So here's me doing that. All I'm going to do is I'm going to plug my eigenvalue into the original matrix where I had lambda. So kind of like this guy up here. Instead of lambda, I'm going to put -1, and then I'm going to put 5 in both of those places, and then I can solve this equation. So here's me doing that. 1 minus -1 is 2, 3 minus -1 is 4, the 4 drops down, the 2 drops down, and this gives me 2 equations that happen to be the same in this case. They should have the same solution, regardless of if they're the same or not. These ones will be the same. And then if I solve these equations, I'd get, so subtracting 2x, dividing by 4, I get y is equal to -1/2 x. And that gives us the vector, and I just said here, like, we could call it v instead of x, because that would be less confusing. And this should be a -1. Somebody caught me in class with that, but didn't fix it here. So our eigenvalue is -1, and our eigenvector, in this case, I put t because it really doesn't matter how long the vector is, it just cares about direction. If you remember a couple slides ago, I said that the eigenvalue is giving you like this stretch. This is an eigenvalue. And the eigenvector is giving you a direction. Direction. I know how to spell things. tends to be that we just like plug in 1 here. So in this case, you'd end up with this is 1 and -1/2. That's your vector. You could also plug in 2 if you wanted to have whole numbers, or 10. It doesn't really matter because you're just getting a direction from this, and your stretch is actually coming from the eigenvalue. If you would like to, you can do the exact same thing with the other, and you should, the other eigenvalue. All I did was, again, plugged in 5. Got my new equation. This is the characteristic. Or not the characteristic, sorry. So this is like a times x equals 0. Got our equations. We solved them. This time we got y equals x. So in this case, for lambda is equal to 5, an eigenvalue of 5, we have the matrix T over T, or probably most people would end up choosing where T is equal to 1, and then they get the matrix 1, 1. Okay, that's a lot. And you don't have to do all of this every single time. I'm going to do a quick example on the next page. Okay, so we say find the eigenvectors and the eigenvalues of this. First thing I'm going to do is set up the characteristic equation. Here is that characteristic equation where you've got 5 minus lambda, -3, -6, and then 2 minus lambda. You're going to subtract lambda down the side. Then we're going to get the determinant of this. So I'm going to multiply these, and then I'm going to subtract off these like this. 5 minus lambda times 2 minus lambda minus -6 minus -3 is equal to 0. Then we're going to distribute and gather our terms. And we get a quadratic. Lambda squared minus 7 lambda minus 8 equals 0, which we can factor like that. And that gives us our solutions. Our first lambda value, lambda 1, is going to be positive 8, and lambda 2 is going to be -1. Okay, then I need to use my characteristic equation again and help me get the eigenvector. So in this case, here's how I'm going to set it up. I'm subtracting lambda off here, so that gives me -3 and -6. Oh, sorry, -3 and -6. Then I can set up the two equations that I've got, which in this case would be -3x minus 3y equals 0, -6x minus 6y is equal to 0. And notice these will both have the same solution, so I'm just going to solve the second one. If I add 6x to both sides, I'm going to get -6y equals positive, oh geez, stop trying to cut corners, Perkins, equals positive 6x, and then you will get that y is equal to -x. This now is how I'm going to get my vector. So my eigenvector in this case, if we make, let's say, t equals 1, right? Because this again is just like a relationship between the two values. If t was 1, then y would be -1. So I would just give me the vector 1, -1. And that again has an eigenvalue of 8. So here's one of the eigenvectors and its associated eigenvalue. Again, do the exact same thing with the other side. Feel free to skip forward here if you don't want to watch this, but we're going to have 5 minus -1, -3, -6, 2 minus -1, x, y equals 0, 0. This is going to get me 5 minus -1 is like adding, so I get 6, -3, -6, 2 minus -1 is like adding, so I get 3. Cool. That's good because I'm going to get the same solutions from those. I'll get 6x minus 3y equals 0, -6x plus 3y equals 0. These both have the same solution, so let's just add 6x, and we get 3y equals 6x, and we get y is equal to 2x, and that would give me the vector, if I plugged in x was 1, that y would be 2, and the associated eigenvalue for that is -1. So, long story shorter, in this case, if I applied the transformation matrix, this, to the entire plane, the whole plane is going to move around a whole lot, right? It's going to stretch out, it's going to stretch out, it's going to be like weird little parallelograms, if you think about that teal thing. But two vectors are not going to go off their span. The vector 1, -1 will stay exactly where it's supposed to be, but everything along that vector will get stretched by a factor of 8. And the vector 1, 2 will not fall off its span, but it will get like flipped around and stretched by a factor of -1. So that is what we get when we have found the eigenvalue and the eigenvector. Let me know what questions you have.